All right, so we're first going to look at magnetic fields. All right, so before we get to anything on these slides, who wants to just give me some information that you remember from this section? What exactly is the magnetic field? What do you know about magnets, magnetic field?
Like charges repel and unlike charges attract.
All right, so I'm glad you said that because that is a misconception that we're going to correct in the lesson. Right? Because what you just spoke about was about charges, and what we're looking at is basically magnets, which most students normally misunderstand between those two concepts. So we're going to look at that deeply. Anybody else?
Opposite poles attract.
Opposite poles attract. All right, so we're here in the CXE part that you learn about magnets. Anything that you learn from Cape level. One thing that you learn from Cape level, and then we can start. Come on, guys. It's going to be easier when we all have a communication. Don't want to just be me alone. All right, so I guess everybody is a little bit shy. So let's start and see if the shyness will disappear. All right, so the first term that we're going to be introduced to is magnetic flux. Now, the magnetic flux is basically the measure of the number of field lines that passes a specific region. All right, so if we take, for example, the two diagrams there, the field lines are the arrows that are being drawn, and the areas we're going to focus on is A and B. Now, we notice that A, the area that it passes through is smaller than the area that it passes through at B. All right, now we notice that 3 magnetic field lines passes through A, and through B we have 6. All right, so what the magnetic flux tells us is that it's basically looking at how much of those field lines will pass a specific area. All right, so that's what the magnetic flux is, which is measured in a unit called Weber, and it is also a vector quantity. All right, and all that's cleared, so we know what to define magnetic flux as. Yes.
Yes, sir.
Yes.
All right, thank you. All right, now let's look at something now. Now we notice these two areas, which are the blue shaded regions. They are different size, but if you notice the amount of field lines through them are the same amount. So question, is that telling us that they have the same magnetic flux, or one has more magnetic flux than the next?
Same magnetic flux.
All right, could you repeat that, please?
The same magnetic flux.
So it's the same magnetic flux, and why do we say they have the same?
The amount of arrows present.
The amount of arrows present in that region. So magnetic flux is not dependent on how the shape of the area. It's only dependent on the amount of field lines that passes through that specific area. All right, so that's what the magnetic flux is. All right, and as we can see here, we have the A and B being the same size, but A, the field lines are more compact, so you have multiple field lines in A, but at B we only have 2. So in A, the density of field lines increases, right? While in B, the density of the field lines are very small because they're very spaced out, right? And that will lead us into the next term. All right, before we go to the term, then we look at the equation, which we're going to look at a little bit more, which magnetic flux is phi, that symbol there with the circle going down with the line vertically through that circle. So phi is equal to BA sine theta. Now B is the term that we're going to look at now, which is the magnetic field strength or flux density. A is the area of the space in which the field lines are acting, and sine theta is if there is an angle between the area and the field lines. Now, if we look back on our previous these examples, This means that if you hold your hand and point your next fingers towards that hand, your fingers represents the feel lines, right? And hence it has an angle of 90 degrees towards the area that it's going to be acting at. So if the angle is 90, then that means sine 90 is 1. Right? So you get the maximum magnetic flux if you are perpendicular to the area. Once you change the angle at which the field lines act on that area, then that means you start getting a reduced magnetic flux. All right, and we're going to use that equation later on in our lesson. And now we look at the next term, which is that B from the equation, which is the magnetic flux density, which is also called the magnetic field strength. All right, and if we go back to the diagram here, we see that A has a high magnetic flux density because even though they have the same size area, we have more field lines in that specific area than B. Right? So magnetic flux density is represented by the symbol capital B, measured in a unit called Tesla, right? And it's the measure of the flux per square meter. This enables us to compare the field strength of the magnets. All right, so the definition that you can use is the number of magnetic field lines of flux that passes through a certain point on a surface. All right, so the flux density is basically the amount of flux in a specific area. Everybody understand so far?
Yeah.
All right, so your syllabus also requires you to define what the Tesla is. All right, and the Tesla we know is the unit for the flux density, which is the 1 Tesla is the uniform magnetic flux density, which acts normally to a long straight wire carrying a current of 1 ampere, causing a force per unit length of 1 Newton per meter on the conductor. All right, so this is a term that you need to know how to define because it's required by the syllabus to define this specific term Tesla. All right, and this is something just to recap from CSEC, which tells us that when you have current flowing in a conductor, it creates or it generates a magnetic field. All right, so the left diagram represents, the pencil represents a conductor with a current that's going upwards in the conductor, and the diagram on the right represents a solenoid, which is just a coil of conductors, and the current, you notice, is going to the right hand side. All right, so how do we know how to get the magnetic field around these conductors? What rule do we use?
Right hand grip rule.
Is it the Fleming's?
No, first person got it. Yes, the right hand grip rule. All right, so the right hand grip rule tells us how the magnetic field will be around these specific conductors. So on the left diagram, sorry, the conductor is just a straight wire. The current is going up, so we grip the conductor with our thumb pointing in the direction of the current, and hence we see that our 4 fingers will curl in that direction that is shown in the diagram. All right, so it curves from left going towards the right side. All right, and then in our solenoid, the same principle applies, but in this case, you're actually using your 4 fingers to show the direction of the current, and your thumb will point the direction in which the North Pole will be created. All right, so we notice your current is going towards the right. So you coil your fingers like you're gripping something with your thumb out, all right, and then you place it just as how it is. So your 4 fingers would be coiling towards the right, and hence your thumb points in that upward motion. So we see that all those arrows are going away from the top part of the solenoid. And the top part of the solenoid will create a pole. Which pole is that? Yes, what pole will be at the top? Anybody? What pole will be generated at the top based on this?
Yeah, I don't understand how you get the solenoid one.
All right, so the solenoid is same right hand grip rule, but the difference in this one is that your four fingers will curve in the direction in which the current is going. And you point out your thumb will be pointing towards the North Pole. So if we grip our hand, like you're gripping something, and then your four fingers point in the direction in which the current is going, which is going towards the right, your thumb points upwards. All right, we try that, we see. Yes, no.
Yes, sir.
All right, so because our thumb points upward, then that tells us that the arrows are pointing up, going away from that side. All right, and because it's going away from the upward part of the solenoid, that part is the what pole? So which pole is generated at the top?
North.
North Pole.
Or North Pole is generated at the top, and hence the arrows going in at the bottom shows that the South Pole is generated at the bottom part of the solenoid. All right, any questions there? Are we all good?
Following so far, sir.
All right, great. All right, so this is just the same. All right, and then we look at the equations. So we use this equation for a wire. So for the left diagram where it's just one conductor straight wire, to find what the field strength, the magnetic field strength or the flux density is at a point, because we know that if you're close to the conductor, you're going to experience a strong force, magnetic force, or magnetic field. If the further you go away from it, then the field strength becomes weaker. Right? So this equation tells us that the field strength is equal to a constant, which is called the permeability, right, of free space, which is given on every question, times the current that is in the conductor divided by 2 pi, and r there represents the distance that you are away from the conductor. Right? And the denominator 2 pi r represents something in math, right? Which is
Circumference.
Circumference.
the circumference. Because as you can see, the conductor creates a magnetic field that is of a circular pattern. Right? So if you want to find the strength at a specific distance away, then it's basically once you find it at that point, if you continue around in a circle around the conductor at that same distance, it's the same strength at any of those points. So that's why they use the circumference equation in that case. So we use this equation for when it's just one wire, and we need to find the field strength at a point away from the wire. All right, we get that?
Yes, sir.
All
Yes,
right.
sir.
Yes.
All right, and now we have a second equation, which is if it's a coil or a solenoid, like the diagram on the right. Right? So we use B is equal to the permeability of free space times capital N times I over 2R, or we use permeability common N times I. Let's look at each individually. Now, the capital N tells us it's the number of turns. Right? So it's the number of turns that are in the solenoid. Yes, a question? Yes, I think it is being recorded. Yes, it is being recorded. So if you want a copy, then you can just email Candice or she will send it to everyone. But it is being recorded, yes. Okay. All right, so the capital N represents the number of turns in the solenoid. All right, and then if we want to use this one, which is a common n. The common n represents the number of turns per length of the solenoid. So you're going to experience some questions that asked to find the number of turns per length, or it asks you to find the number of turns. So depending on the structure of the question, it tells you which of the equations you should use. All right. Any questions there before I move on? All right, so please remember these equations because we're going to use them in the tutorial session with some questions. All right, so just to easily use these equations, let's get our calculators out, pens and paper, and let's just work these as quickly as possible. All right, so what's the magnetic field strength at the center of a solenoid, which has 2,500 turns of wire, is 25 centimeters long and has a current that's flowing through it as 3.6 amperes. All right, so giving you 2 minutes to attempt that. All right, so remember the permeability of free space is, all right, let's just give you, when you calculate the pi in it, it is 12.56 times 10 to the negative 7. So 12.56 times 10 to the negative 7, that's the permeability of free space. Once you get an answer, you can just write it in the chat.
Sir, could you please repeat the permeability of free space?
That's 12.56 times 10 to the negative 7. All right, let me just go back to the formula. So remember the formula is B is equal to permeability, N, which is the number of turns per length, times I, or its permeability, number of turns, times current over 2R. So this or this. Not seeing any answers. All right, there we start getting yet. Remember values have units, so please practice to attach units to it. All right, one more minute, and then we move. All right, so I'm seeing persons getting the correct answers. That's good. All right, so that tells us that the equation that we used was which one? This or this? This or this one? Which one did we use?
The other
Sir,
one.
B equal
Yeah, that one.
permeability.
All right, so we use this one. All right, because it gave us so it gave us current, it gave us the length of the coil, which tells us it's a long coil, so we can use this. But the common N, all we did was to replace it with the number of turns over the length. All right, so your full equation would be 12.56 times 10 to the negative 7 times the number of turns, which is 2,500, times the current, which is 3.6, divided by the length of the solenoid, or the which is 0.25 in meters. All right, so we get 0.045 Tesla. All right, so we use this one, Simone, which is the magnetic field strength is equal. All right, let me try it on the whiteboard. All right, so the equation that we use was B is equal to mu naught Ni. All right, because the question gave us the length of the solenoid, which tells us it's a long solenoid. But we know that the N is the number of turns over the length. So we can replace N with that equation, so it becomes now mu naught Ni over L. And hence this is 12.56 times 10 to the negative 7 times the number of turns, 2,500, times the current, which is 3.6, over the total length of the solenoid, which was 25 centimeters, and we change it to meters. And hence we get 0.045 Tesla. All right, get that now? For all those who had little problems there.
I understand now. Thank you.
All right, no problem. All right, so let's look at, I think there's another question there. All right, here we go. So this one now asks us which, we have a solenoid which has a current of 5.2 amperes of current through it, has a magnetic field strength of 0.35 Tesla at its center. How many turns per meter does this solenoid contain? All right, so this one should be a little bit easier, so giving you just 1 minute. All right, so I have one answer so far. All right, no more answers. Just have one answer so far. All right, so it looks like everyone is getting. All right. So again, we use the same equation because now we're asked to find the number of turns per meter, which that tells us we're finding common n. So therefore, common n is B over permeability times current. And B is 0.35 divided by permeability, 12.56 times 10 to the negative 7 times current, which is 5.2. And hence we get 53,589 turns per meter. Any questions for this one? Or are we all good? Yes, should I do it on the board or we're good?
Sir, can you do it, please?
Yes, sir.
All right, let's go. All right, so here we go. So according to the question, we're given B, which is 0.35. All right, we know permeability is 12.56 times 10 to the negative 7. And we're given I, which is 5.2 amperes. All right, we need to find turns per meter. All right, and turns per meter is common N. All right, just turns is capital N, turns per meter is common N. So hence we're finding N, and we know B is equal to mu naught N I. So N would be B over mu naught I. All right, and B is 0.35. Mu naught is 12.56 times 10 to the negative 7 times current, which is 5.2. And hence we get 53589 turns per meter. All right, understand now?
Yes, sir.
All right.
Can you go back to the question, please?
All right, so we will be doing more questions at the end. So we're just going to skip through these questions because they're just using the same equations. So we're going to look at that at the end. All right, so that's the end of magnetic fields so far. So we learn about flux, magnetic flux density, wire, or if it's in a solenoid or a coil. All right, any question before we go on to magnetic forces? Was that a question? Because it just went in and out. All right, so I guess not. So we can go now to magnetic forces.
Sir, excuse me 1 minute.
Yes, go ahead.
Is it that the equation for a long solenoid is different from that of a single wire?
Yes, it is. So for the single wire, it is B is equal to mu naught I over 2 pi r. So this is just for a wire like that. But once you start to form a coil, then we use the other equation that we have been using, All right, answer your question. All right, so now let's go to magnetic forces. Magnetic forces, which tells us that what's the force exerted on a a charge or on a magnet by another magnet based on a magnetic field. All right, so that's what we're going to focus on. So this here is something that we should all remember from CSEC or Fleming's left-hand rule. But without reading what's here, when do we use this left-hand rule? Yes, nobody? When do we use Fleming's left-hand rule?
Try to find the direction of the force.
So trying to find the direction of the force. All right. So it's to find the direction of the force that is on a conductor or on a charge. So basically on a charge that is inside a magnetic field. All right. So once a charge is moving inside a magnetic field, we use Fleming's left-hand rule to find the direction that the force will be acting on that charge or conductor. Now the question is, why do we have a force that is present? So why is it that when a conductor is in a magnetic field, there is a force that's created on the conductor?
Sir, because of the current going through, passing through the magnetic field.
All right, so the conductor has to have a current, yes, but what does the current do? Why the current is so special that it creates the force to be created?
It's an induced force. It's an induced current, sorry.
No, it's a current from a source, current. It has a magnetic field of its own, all right? So we're starting off. So because, remember we just did that conductors have a magnetic field around them because you have current through it, all right? So that magnetic field will do what? Yes, anybody? That magnetic field around the conductor will do what?
Cause an attractive or repulsive force.
So it will cause attractive or repulsive on the external magnet. Right? So it interacts with the external magnetic field. And we know that when you have two magnetic fields coming together, you either get a repulsive or an attractive force. So that's how the force is created. All right, and you need to know that. So the force is generated because the magnetic field around the conductor interacts with the external magnetic field of the magnets. And once you have two magnetic fields interacting, then it creates a force. All right, and then we know the force direction is dependent on Fleming's left-hand rule, which states that your index finger points in the direction of the magnetic field, which points from north to south. All right, your middle finger points in the direction of the current that is moving, and your thumb points in the direction that the force is going. Now, the current direction, the charge that should be moving is positive charges. So Fleming's left-hand rule gives you the direction of the force on positive charges. So what if it was an electron that was moving? What would you do to find the direction that the force will be going on an electron?
Repeat that.
Is the opposite direction.
It would be the opposite direction. So if it was an electron moving in the conductor, when you use Fleming's left-hand rule correctly, the direction you get is just the opposite direction for an electron, because Fleming's left-hand rule only gives you the direction on the force on positive charges. All right, so that's something that you need to make note of, because they sometimes will like to change it around and say an electron. All right, so you need to know if it's an electron or if it's a proton. The proton works the same way, but electron, it would be the opposite direction. So here we have a conductor between the poles of a magnet. To find that force, the quantitative force, we use the equation F is equal to, we normally write it in the Bill format. So BIL, easy to remember. So F equals BIL times sine theta. Now sine theta is basically the angle between the conductor and the magnetic field. So if there's an angle that is created between the conductor and the magnetic field, that will be the theta. Now to get the maximum force, theta is normally 90 degrees. All right, so normally the magnetic field is going, in this case, from left to right, and then the conductor will be going from up or down. All right, so you get a 90-degree cut between those two, and you get the maximum force. But if it's not 90 degrees, then you need to include the sine theta part that shows you that the force is reduced. All right, so the force on a wire that's between magnets is calculated by Bill, F equal Bill, where B is your magnetic field strength of the magnets, I is the current, L is the length of the conductor inside that magnetic field. All right, and if there is any angle between the magnetic field lines and the conductor, then you add the sine theta part to it. Any questions there?
Sir, I
All
have
right,
a question. Can you repeat what you were saying about the electron?
Oh, sure. So the Fleming's left-hand rule is used for positive charges. So when you align your index finger and your middle finger, it points in the direction of the positive charge. But if the question is saying that it's a negative charge, like an electron, then all you need to do is just to reverse the direction that you get for your force. So if you got that the force is going up, then if it's an electron, the force will be going down. Right?
Okay.
So the normal direction of the left-hand rule is only for positive charges. So if it's negative charge, you still do the same thing, but it's just that when you get your thumb pointing up for negative charges, it would be pointing down. Get that?
Okay, okay, sir. Yeah.
All right, no problem. All right, and then the other part equation at the top, where F is equal to QVB, that's if it's not an entire conductor, it's just a charge. Right? So instead of a wire that's between the magnets, we just have a single charge that is moving in the magnetic field. Right? So if we just have an electron, or we just have a proton or one electron moving between a magnetic field, then a force will be generated. And that force is calculated by the value of the charge times the speed that the charge is moving times the magnetic field strength of the magnets. And again, the angle would be if there is an angle created between the magnetic field and the direction in which the charge is going. All right, we get that? So you need to know the distinctive difference between when do we use Bill and when do we use QVB. So QVB is when it's just one single charge, no conductor is present, just a charge moving. And Bill is used when it's a conductor that's carrying current. All right, so ensure you meet that distinctive difference when you're using these two equations. All right, now this here, they require you to know some uses of electromagnets. All right, so I can just share what this thing takes us to, so we can see some uses that we use electromagnets. But while I'm doing that, anybody can tell me at least one use for electromagnets? Nobody? One use that we use electromagnets.
Sir, we use them in headphones.
Certain generators.
Headphone, motors, doors,
Generate.
automatic generators. All right, so I guess we don't have to go through these. All right, so this link, let me just share it with you guys so you can have it on your side. All right, there you go. All right, so this link just gives you a little bit more in depth. So you see you have your motors, and motors are in fans, any cooling system. All right, electric bells, your speakers, so your headphones that somebody said. All right, for industrial uses, using sensors. All right, so all these are just uses of electromagnets. in medical uses. It can be used in MRIs. Alright, so that's why you don't do MRI with any form of metal present. Alright, so you just need to know preferably at least 4 uses of electromagnets from any of those that's listed there. Alright, it's good to know at least one from each different industry. So industrial use, medical use, it's good to know them like that. Alright, so now let's look at the force between two parallel wires. So if we have two wires, two conductors that are close together, carrying current, the conductor 1 will have a magnetic field around it, conductor 2 has a magnetic field around it. They are close together, so that means their magnetic fields will interact, and that interaction of the magnetic fields will produce a force. Right? So that force is what we're going to calculate. Right? So the force, and the reason why it's F over delta L, the delta L is just for the length in which we're focusing on. Because sometimes it's an entire wire and we just want to focus on a specific part of it. Alright, so it's basically F is equal to permeability, current 1 times current 2 over 2 pi r. Alright, so that gives us the force that is between two wires that are interacting with each other. Now the force can be a repulsive force or the force can be an attractive force. Alright, so we see that to produce an attractive force, the currents in the wires should be going in the same direction. And if it's a repulsive force, then they should be going in opposite directions. So those two things are important. So if the current in both wires are going in the same direction, then that gives us an attractive force between them. So both wires will be attracted to each other. Alright, and if it's a repulsive force, then that means one current is going one direction, the next current is going the opposite direction. So you get a repulsive, so they're trying to push each other a little away from each other. Alright, we get in that. Any questions so far?
So how we do when it's a repulsive force? Would they state that the current is going in opposite direction?
Wait, go again, please.
How do we
Repeat
know when it's
question.
an attractive or repulsive force? Would they state the direction of the current in question?
Yes, or the diagram will be there.
Okay,
So,
sir.
alright, so question is why are they attractive when currents are going the same direction? Alright, let's see, I think the next slide. So here we go. So here we have in both situations. So we're explaining why they are attractive and why they are repulsive. Now the diagram on the left shows that they're going in the same direction. Because remember, when it's just a X, it tells us that the current is going into the paper. When it's a dot, it tells us that the current is coming out of the paper. Alright, so in the left diagram, we have two conductors where the current is going into the paper. Alright, how do we know the magnetic field around it? We use a Fleming's right-hand grip rule. So if you're going into the paper, your thumb should be pointing towards the screen, and then you notice that your magnetic field lines will be going in a clockwise manner. Alright, so in both of the wires, there's a clockwise rotation of the magnetic field. Everybody get that?
Go again, sir. Go again.
So we're just looking at the left diagram. So we have two conductors that send in current into the screen. Alright, so we use Fleming's right-hand grip rule, where the thumb points in the direction of the current. So the thumb will be pointing into the screen, and your four fingers will coil in a direction that is clockwise.
Yeah, so far.
Alright, now what's not shown here is what we're going to look at. Let me just bring up the whiteboard, which is when that happens. So this is conductor 1, And when that happens, it's going in that direction, a clock. Sorry, not that. It's not clockwise. It's going the opposite for that. Where is? So this is your, and it's going clockwise. All right, and then we have conductor 2, same direction. So magnetic field, it's also going clockwise. All right. So now we are going to see that we put a compass at these 2 points. We're going to show you why it's attractive or repulsive. If we put a compass here, we notice that this magnetic field is going downwards into the compass. All right. So we're just treating these circles as a magnet. According to a magnet, all right, whenever the magnetic field lines are going away from that side, that's a north pole. When they're going in that side, that's a south pole. All right. So this side is coming in. So that means it is a south that's there. All right. And then this side is going out. That means a north that's there. So imagine these 2 wires touching. What do you notice?
Attractive forces.
Exactly, because north and south coming together, you get attraction. Well, see that?
Clear and all.
Hi, everybody else?
Yes,
All
sir.
right. All right. So the same principle would apply if it was opposite charges, if it was opposite direction, sorry. So again, one would be going this way, and then the other one is a dot, so the opposite direction. So this magnetic field will be going that way. So if we treat it as a magnet right here, so into this side, it will be south. Into this side would be south. South and south coming together, you have repulsion. All right, so that is the reason why you have an attractive and repulsive force depending on the current direction in each wire. All right, and here we have an effect that's called the Hall effect. And the Hall effect is so if we have an electric current flowing through a conductor in a magnetic field, the magnetic field exerts a transverse force on the moving charge carriers, which tends to push them to one side of the conductor. A buildup of charge at the sides of the conductor will balance this magnetic influence by producing a measurable voltage between the 2 sides of the conductor. All right, so in simpler terms, what this is saying is, let me just go to the next diagram, which explains it. Once you have a conductor that is between the poles of a magnet, right, it's going to cause the charges inside the conductor to separate, right? Meaning that it's going to push the negative charges to one side, push the positive charges to one side. And we know why, correct? Why would it cause the charges to be separated?
Sir, can you repeat again, please? I didn't hear.
All right, so I'm saying when you have a conductor between the poles of a magnet, all right, it's going to cause the positive charges in the conductor to push to one side and the negative ones to push to the opposite side. Now the question is, why is that happening? So why the positive go to one side, the negative goes to the next side?
Sir, sir, is it due to the magnetic force?
So it's the magnetic force. So the same thing I would just explain to say that there is a force created because you have charges moving, all right? And we know why they don't go in the same direction, because there are 2 different charges. So positive, remember Fleming's left-hand rule works for positive, and if it's negative, then it goes the opposite direction. So in this case, these positive will go to the right, and hence the opposite will happen to the negative charges that will push to the left. So now we see that the conductor has a change in potential or change in charge value, because Most of the negatives are on the left side, most of the positives are on the, the right side. So hence we have a potential difference between these two charges that are inside the conductor. So that's basically what Hall effect is. So Hall effect is basically just telling us that there is a potential difference that's generated inside the conductor because the charges get separated due to the force that the magnetic field has on the conductor. Are we clear? Yes. Any questions?
So that one more time, sir.
All right, no problem. So the Hall effect tells us that there is a potential difference or a voltage that's generated inside a conductor due to a magnetic field that pushes the positive charges to one side and the negative charges to the opposite side. All right, so that's what the Hall effect quantifies. All right, so you have what is called the Hall voltage. So the Hall voltage is that difference in the potential between the positive charges and the negative charges.
All right, respect.
And this is just exactly what I just said, so I don't have to go through it again. All right, and the principle is taken from this simple, well, not really simple setup, but it's a simple setup of what is called a Hall probe, which demonstrates this same process. Now, to measure this voltage that's inside the conductor between both ends, between both sides of the conductor, we normally use a very thin sheet of conductor. So normally, if you guys go UE and you do physics, because I did this when I was at UE, they use a foil paper. All right, so it's very thin. All right, so we use a foil paper that is thin and it is of a specific width, so we can measure the voltage between one side to the next side of the foil due to the Hall effect. All right, now just note the voltage that will be measured is a very small voltage, so it's not going to get a very high voltage due to this effect. So that's what the Hall probe does, is to measure that voltage that is generated in the conductor. We're not going to look at these questions. No, we're going to just do them in the tutorial session. So we have 15 minutes to do the last set of slides, which is magnetic induction. Before we go to that section, anything about magnetic force? Do I need to repeat, or we're all clear in magnetic forces?
So we're good. We're good.
Okay. All right, so the last thing is the magnetic induction, which is nothing to do with calculations. So magnetic induction. So all we've learned so far is we have a conductor, we have current in the conductor that is inside a magnetic field. So it experiences a force. What we're doing now is slightly the opposite of that. We have a conductor that's inside a magnetic field. It don't have current, and we want to give it current. So that's what magnetic induction is. So you're giving current to a conductor by the use of magnets. All right. Now, to do that, the value of that current or voltage that will be generated is dependent on three things, mainly two. The last one is not that big of a difference when we do it in the lab. The speed at which you're going to move the conductor or the magnet, and the strength of your magnet. Now the shape of the wire takes into, are we using a coil or are we using just a straight line conductor? All right, and we're going to look at those effects now. All right, so now there are two laws that governs electromagnetic induction. First one is Faraday's law. And Faraday's law tells us that the induced voltage or current in a coil is proportional to the rate of change of magnetic flux linkage. Anybody wants to just break that down in the simplest form? What is this saying? Come on, nobody wants to attempt? What is this Faraday's law stating? I guess nobody wants to go. All right, so what this is saying, so if we look at the diagram keenly, we know that we have the flux, the magnetic flux, the field lines going from north to south. All right. Now, when you introduce a conductor to that, when you move the conductor inside that magnetic field up and down, you're actually cutting those field lines, which is your flux linkage. All right. So the faster you move them, the conductor, the faster the field lines are cut and can be rejoined. So that's what the rate of change of magnetic flux linkage is. How fast are you cutting those field lines so they get disconnected and then rejoined after you move it? All right. So Faraday's law is telling us that the current that will be induced in the conductor is proportional. So that means if you're moving the conductor slowly, then it's going to cut the wires slowly. Hence, the current that's induced will be slow or low. If you do it faster, then the rate at which you're cutting them increases, and hence it increases the voltage that's induced. All right, clear?
Yes, sir.
All right, so that's what Faraday's law tells us. So Faraday's law gives us evidence that there is an induced current or voltage that is produced when a conductor cuts the magnetic field lines of the magnet. Now, the important part here is that you have to cut the field lines. Right? So in this example, if the person was moving the conductor from left to right, would that create an induced current or induced voltage?
No, because it's not cutting the field lines.
Exactly. So if the conductor is moving with the field lines, it's not cutting the field lines, hence there is no induced current produced. So the only way you can have induced current is if the field lines are getting cut. It can be cut at any angle once it is being cut. The angle to get the maximum induced current would be what? What
90
angle would
degrees.
Normal 90 degrees.
90.
the 90 degrees? Alright, so 90 degrees to the field lines, you're moving your conductor, you get the maximum voltage induced. Alright, now to know the direction of the current that is induced, we use Fleming's right-hand rule. So now, remember, before we use the left-hand rule to find the force that is on the conductor, now Fleming's right-hand rule is to find the direction of the induced current inside that straight wire conductor. Alright, so again, the index finger represents the field, the magnetic field. The middle finger is for the induced current, and their thumb is for the motion. Alright, so in this case, the field line is going to the left. Alright, if you're pulling the conductor upwards, then your thumb will point up, and hence your middle finger will point, telling us that the current will be coming out. So the induced current is coming out. But if the conductor was now, it went up and then it's coming back down now, then that means you change your thumb pointing downwards, and hence your induced current will go away from you. So that tells us if you continuously change the motion of your conductor, the induced current will continuously change its direction. Everybody get that?
If you change the direction of the conductor, the induced current will change. What?
So the induced current direction will change.
Oh, okay,
All
sir.
right. So if you put the conductor down, the current goes one direction. If you put it up, the current changes and go the opposite direction. All right. So that's what Faraday's law tells us: the existence of induced current because we're cutting the magnetic field. Alright, so that tells us the speed at which it goes increases or decreases the induced current. And then we have the second law, which is Lenz law. Now, Lenz law tells us it's mostly for coils. So if you're looking at a coil and we need to induce current inside the coil by putting a magnet into the coil, the direction of the induced current is created to oppose the change that is causing the magnetic field to be, or the induced current to be created. And what that means is that when you're putting in a magnet inside the coil, or you're taking out a magnet out of the coil, the coil will generate a magnetic field so that it opposes the change that's causing it. And we're going to look at it in a simulation. All right, so that's what Lenz law does. Lenz law tells us about the direction of induced current in a coil. All right, so that first bullet point there, you need to know it, because if it asks you to state induced current, Lenz law, you need to know what Lenz law is. All right, so Lenz law tells us the direction of the induced voltage is such as it causes the effect to oppose the change producing it. Now, to find the direction of the induced current in the coil, we are going to use what is called the left-hand grip rule, which operates the same as the right-hand grip rule. Now, let's go to that simulation. Let me give you the link. So if you want to bring it up on your side, you guys have used it in your classes before. All right, there you go. So in all magnetic induction, this is probably the hardest part for most students to know. How do we know what direction it is? So now here we have our magnet, we have a coil, just a bulb to prove that there is a current that is induced, and we have a voltmeter. All right, now you notice the voltmeter can go to the right or to the left depending on the direction of the current that's flowing through it. Now let's go. So let's predict before we do it what direction. If we're going to put a north pole into the coil, let's use Fleming's left-hand rule to prove what direction it will go. So according to Lenz states that the coil, because we have a north pole coming into the coil will generate a magnetic field of itself to oppose that motion. So how can you oppose a north pole coming into the coil?
They produce
What's that? Didn't hear.
a force in the opposite direction. Like
A force that come out of it.
So it needs to oppose that motion. So it produces a repulsive force. So therefore, to repel a north pole going into the coil, then the coil needs to create a north pole where? Left or the right side of the coil?
right.
Right?
On the right hand side. So that means on the right hand side of the coil will induce a north pole there, and hence when this magnet north pole is coming to it, it's going to try to push it back away from it. Everybody understand that part so far?
Yes, sir.
All right, so now that we know where the induced magnetic field will be on the coil, we can use the left-hand rule, which is just to grip again. The thumb will point in the direction of that induced north pole. So we notice the north pole will be on the right side of the coil, so our thumb will point towards the north, towards the right, and then we wrap our fingers, curl it, and we see that the current will be going in this manner in the coil. And based on that motion of the current, would it go to the negative? Would the pointer flex to the negative or to the positive of the meter? So just continue the current flow until it reaches up to the meter and tell me which direction would it flicker, negative or positive side?
Sir, could
Nobody?
you please?
So I'm saying, what direction would the pointer flicks in the meter? Would it go to the negative or to the positive side?
Negative.
To the negative. All right. So if we just take the last coil that's on the left side of the coil, it's going to go downwards, and then through that one, it goes from the positive to the negative. So therefore, the pointer will flick to the negative when we put it inside the coil. All right. You notice if we go in slowly, the pointers just flickers slowly. If we go in fast, it flickers fast. So the speed affects the induced current. Now you notice that if we're taking out the magnet, it goes to the positive side. Why, when you're taking it out, it changes direction?
Sir, because the magnet going in the opposite direction, that means the opposite
Because
force.
I will change into
So the induced magnetic field will now change because it's now need to oppose that. So if the North Pole decides, hey, I'm leaving, the coil will want to oppose that leaving to attract it back to it. Right, so it now changes the magnetic pole on it, and hence it changes the direction of the induced current. Everybody understand?
Yes, sir.
All right, so that's basically what Lenz's law is and what Faraday's law entails. All right, and that's the end of magnetism and electromagnetism lecture part. So we're supposed to go through some tutorials. So if you have no questions, I'll just give you a 10-minute break, and then we start the tutorial session. Any questions? All right, no questions. All right, so we're going to restart in 10 minutes, which is at 11:42 on my side. So 11:42, we resume with the tutorial session. So you don't have to leave, but please be here by 11:42 so we can start doing some questions. All right, see you guys then.